Oh God, Joe, are you okay?
I don't know, bro. I think I just experienced a high rate uniaxial load on my lower lumbar spine, man. I can't feel my legs.
Luckily for you, we've actually been researching this.
Your spinal cord is a long, thin, tubular structure made up of nervous tissue that extends from the bottom of the brainstem down to the bottommost lumbar vertebrae. It's encased in pia mater, a thin protective membrane that acts as a cushion. Within the spinal cord are strands called axons, which carry the sensory signals that provide the motor function and sensation to your body.
But wait, what happened to me then?
Well, you see, Joe, you suffered an impact which directly led to brain damage within your spinal cord, disrupting the axons, thus cutting off connections from your brain to your lower body, leading to paralysis. But you're not alone, with 500,000 people suffering from spinal cord injury annually.
Someone mentioned paralysis. In order to characterize the damage Joe sustained to his spinal cord compared to a healthy patient, we can further simplify our model. We can break down the model out as a solid cylindrical shaft, the blue marking the pia mater, the black marking the physical spinal cord, and the red marking the scar tissue forming as a result of the damage Joe sustained. Furthermore, we are analyzing only a single compressive force, so we are assuming uniaxial loading. And also we're going with lay-high conditions, linear, elastic, homogeneous, and isotropic conditions. Our variable input factors will be the radius of the spinal column cord, the radius of the pia mater, the Young's modulus of the spinal cord, the Young's modulus of the pia mater, and finally our fifth and final variable input, the compressive force exhibited by Joe's fall. So with these 5 input variables, we can now determine the axial stress experienced by the pia mater and by the spinal cord. So for the cross-sectional area of the spinal cord and of the pia mater, we use literature to determine approximate ranges, which we limited down to 1.5 centimeter diameter for the spinal cord and 200 micrometers diameter for the pia mater. For the Young's moduli, we just went through literature once again and determined it through cadaver testing and other scientific methods. Now, using these equations here, we can determine the axial stress for at the pia mater and experienced by the spinal cord. And because we had uniaxial loading conditions, we can simplify the max stress handled by these 2 components here as essentially double the respective stresses.
Now in Joe's case, his spinal cord is damaged, possessing a cavity of scarring tissue. Recent breakthroughs have shown that scar tissue is actually softer in the spinal cord, contrary to popular belief, thus possessing a smaller Young's modulus. With a smaller Young's modulus from the scar tissue, Joe's spinal cord overall will not be as rigid, thus possessing a overall smaller Young's modulus, making Joe susceptible to further damage.
However, our Lehigh assumption is not entirely accurate, as the spinal cord is neither linear or entirely homogeneous. And our uniaxial loading is oversimplified, as our model only deals with compressive loading.
Don't fret though, Joe. Zebrafish, which have the ability to regenerate from spinal cord damage and are similar to mammalian molecular pathways, could provide insight into one day being able to repair spinal cord injuries. We'll need to understand the chemical triggers within the spinal cord better, but in terms of mechanics, the soft scar tissue might help with rebuilding one day.